So before starting, recording. So before starting, let me introduce our speaker, Professor Yusuke Yamada from Waseda University. He received a PhD from Waseda University at 2016. After that, he experienced a postdoctoral fellow at KAU University until 2016, at Stanford University until 2019, and a JSPS Fellow PD at the Rescue of the University of Tokyo until 2020 this year. Since this year, he has been assistant professor at the Waseda Institute for Advanced Study. He is doing researches on the Beyond the Standard Model theory and cosmology. Today, he is going to talk about the QFT description of particle scattering during preheating. So could you please share the screen?
Yeah, okay. Yeah, thank you very much for very kind introduction. Okay, now can you see my screen?
Yes, I can see it.
Okay, so, and okay, let me close.
Yeah, I can see the pointer.
Okay, good. So now let me start. Yeah, today, so I'm Yusuke Yamada from Waseda University, and today I will talk about the QFT description of particle scattering during preheating. And this talk is based on this paper with Taya at the weekend. Actually, he's working on strong field QED. He is not a cosmologist, but we had a very interesting application of some formalism in strong field QED to cosmology. So this is yeah, something like that. Okay. Anyway, let me start. And okay. So, okay, good. So I think this group is like a group of cosmology. So I don't need to say much about the history of the universe, but this is current understanding of the history of the universe. And oh, by the way, if you have any question, please interrupt me whenever you like. Yeah, I'm very happy to answer your questions. So anyway, so this is a current understanding of our the history of our universe, and so we believe that the universe starts from something, and we don't know yet how it starts, but after that, universe experiences so-called inflation, that is the accelerated expansion of the universe. And then eventually, somehow the universe becomes hot through the so-called reheating process. And it becomes what we see now. This is a very schematic story of the universe. So, and basically what I will focus on today is about the preheating or reheating phase. And so from a modern viewpoint, we need some area of the reheating where the energy of the inflation or inflaton is transferred to the light particles. And this process, understanding this process is very important for us to describe the whole story of the universe. So, but it's not so trivial question, because in general, so what we need to know is the energy transfer from inflaton field to the light element. But in this era, especially in the very beginning of the preheating stage, where the inflaton field oscillates, and then and also we have expansion of the universe. In that case, particle scattering process is not like the standard QFT calculation in flat spacetime. So what I will discuss is this kind of difference. I mean, we discussed the particle scattering in a non-trivial background. So what is the difference? And the difference comes from the effectively classical background, such as like inflaton field or gravity. So in that case, we have a very different picture of the scattering. So we need to care about that. So let me repeat what is non-trivial in such a scattering problem. So first of all, the preheating corresponds to some like a non-trivial particle production from the vacuum, which I will explain later. And also, in the non-trivial background, the mass of the particle or couplings can be time dependent. So that leads to the express breaking of the time translation symmetry. And this never occurs in the flat spacetime. So in that sense, these scattering process have a different feature from the standard QFT calculation. So in that sense, we should be clear about if the kinematic approaches such as the Boltzmann equation works or not. Also, mostly we may use some of you think that you can use the scattering amplitude calculated in flat spacetime to the cosmology, but it might not be the case. So we should be careful about when we can use the knowledge about of the flat spacetime results and so on. So this is a very non-trivial point of the scattering problem in non-trivial background. And also, this is independently of these things. This kind of scattering problem is interesting from other contexts as well. So like a strong field QED where you have like a strong electric field background or magnetic field background, and also some black hole, QFT around black hole. And this strong field background leads to non-trivial particle production. For example, in a strong field QED case, we know the Schwinger effect, where the electron and the positron pairs are produced from the vacuum due to the presence of the background electric field. Also, in the well-known Hawking radiation is the consequence of this kind of effect. And yeah, around the black hole is not really black, and the black hole actually emits some particles that is known as a Hawking radiation, and so on. So this kind of topic is relevant to these things, and we can apply the if we can develop the understanding of these scattering problems in cosmology, we can apply it to the other contexts as well. In that sense, this is a very important issue. All right, and today this is the process which I will focus on today. So basically, we assume some inflaton background, and it oscillates around some potential after inflation, and then some particle coupled to the inflaton background produced from the vacuum. And what I will focus on is, so usually this process, the production of the chi from the vacuum corresponds to the preheating. But today, what I will focus on is the fate of chi. Namely, we assume some like a coupling between the chi and other particles, and I will discuss the scattering process of the chi and psi. This is what I will discuss today. And this is a very simple model, but still we can see many interesting non-trivial behavior. All right. So this is my talk plan. First, I will talk about free quantum fields in time-dependent backgrounds, and mostly I will focus on the so-called preheating. So this is just a review of the preheating. And then I will discuss the main topic, the QFT description of the instant preheating. So I haven't introduced the word instant preheating, but basically instant preheating corresponds to this kind of process. And then I will summarize. All right, so let me start with the very basic point, preheating. So for concreteness, I will assume some specific model. So now the background metric is given by the flat FRW metric. And now the inflaton dominates the universe. Inflaton oscillation dominates the universe. Then it behaves like a matter. So the scale factor behaves like this. And I will consider some quantum field chi, which couples to the inflaton in this way. Now this inflaton field is assumed to be just a classical background, effectively, and due to the Hubble friction, the inflaton oscillation behaves like this. So it's like a damped oscillation. And the non-trivial point is that from this action, you can immediately see that the Hamiltonian of this field chi is time dependent. So you cannot ignore this non-trivial effect. And in general, if Hamiltonian is time dependent, we cannot define the energy eigenstate. So there is no unique vacuum state. This is a very starting point of this kind of phenomena. So I have no time to discuss like general things about this issue, but yeah, you can look at some like a textbook by Ward or some other textbooks about QFT in curved spacetime. So because of the non-uniqueness, we have we find some like a particle creation from the vacuum. This is very known from the earlier work by Parker, for example. And yeah. So okay. And preheating was first proposed by Kaufman, Linde, and Stravinsky in 1997, or almost more than 20 years ago. And so what we will discuss is the behavior of this free scalar field. Now, this phi is just a classical background. So in that sense, this is just like a dressed free particle, and there is no interaction of chi. And to simplify this action, we just introduce the substitute this metric, and you get this kind of expression. Now, this time-dependent mass behavior looks like this, and h is a Hubble parameter. And now we can formally quantize this action, this chi field like this. So because the space direction is homogeneous, so it's it has like a spatial translation invariance and so on. So it's easy to the spatial dependence is very simple, plane wave. But the time-dependent part has some non-trivial behavior because of the time-dependent energy. So now the mass is time-dependent, as well as the momentum is diluted by the redshift. So the energy of the particle is given by this time-dependent form. And if there is no time dependence in energy, we can easily find the solution to this model equation. And usually we call Fp given by e to minus I omega pt as a positive frequency mode, and its conjugate to be a negative frequency mode. And then if this is the case, we can like find the quantum field expansion in the flat space-time. But now, because of this non-trivial time dependence, this kind of separation is impossible. Yeah, so positive and the negative frequency modes cannot be separated in a unique way. So this is some consequence of the no energy conservation. And because of this kind of mixing, sorry, the non-uniqueness, we find like a particle production from the vacuum. Okay. Oh, by the way, are there any questions so far? No? All right. So let me continue. So far, we just had this kind of quantum field, and we just formally quantize this one. And the next task is to solve the mode function for the FP. But because the inflaton behaves like this, the mass of the inflaton behaves like shows the damped oscillation. So in general, we cannot find any like analytic solution to the mode equation. So we need to some approximation, and what we use is the following. So basically, first, we just focus on the inflaton field because the amplitude or effect of the inflaton background is the most dominant part. And so we just neglect the Hubble expansion. And also, the effect of the particle production becomes very large at the very first time of the inflaton oscillation. And so we just approximate this damped oscillation by this quadratic form. Then we can expand this time-dependent mass in this way. There's some like a quadratic function of time. And so in under such approximation, we can easily solve the mode equation. So this is necessary to get some analytic solution. And this kind of approximation is okay if the zeta phi squared max corresponds to the maximum value of chi, this one. And sorry, the most important thing is that if the bare mass of chi here is sufficiently larger than the Hubble expansion at that time, then we can neglect the expansion of the universe. And in that case, independent of whether this is larger or smaller than this mass, we can use this kind of approximation. Okay, so this is our approximation. And now what we need to do is that solving this mode equation. And because the effective frequency now is very simple, so I just neglected the redshift as well as the very complicated damped oscillation part. So the effective energy is just like constant plus quadratic term of the time t. Now, technically, we can solve this equation in terms of the so-called parabolic cylinder function, but it's very complicated. But you don't need to know the detail of this function. The most important thing is the asymptotic behavior of this function. So, yeah. Anyway, so what I want to emphasize here is that under this approximation, we can get some exact solution. And this still shows interesting behavior. So the most importantly, so this function shows non-trivial behavior in asymptotic. This function has a very non-trivial asymptotic behavior. And first, if you take t to be minus infinity, or the sufficiently past, then the previous mode function, this one, asymptotes to the this positive frequency mode of the WKB solution. Now the FP WKB is given by this one. This is just a WKB solution. And the FP WKB corresponds to the positive frequency mode. So just in case, let me remind you that positive frequency mode is given by minus I omega p t. So it's just a kind of generalization of the flat space-time case. Anyway, and now, if you take t to be plus infinity, you find that the same function fpt behaves like this. Now, the alpha p or beta p are like some constant depending on the momentum p, and that satisfies this kind of condition. And the FPWKB or the FPWKB star is given by this one or its conjugate. So the most important point is that in the past infinity, the FPT was just a positive frequency mode. But in the asymptotic future, the mode function behaves like a mixture of the positive and the negative frequency modes. So this is important because, yeah, let's see what's going to happen under this behavior. So first, in the past infinity, we can define we can expand the quantum field like this, because the mode function fpt becomes just like a positive frequency mode, so it behaves like this. On the other hand, if you expand the quantum field at near the future infinity, you would find other different expansion. So now this is the creation and annihilation operator in the past, but you need to define the creation and annihilation operators in a different way. And these A in and A out are related to each other by this kind of relation. So alpha p and alpha beta p star, etc., are like some constant defined previously. And this means that if you start with some like a past vacuum state, which annihilated by this past annihilation operator, then in general, because the A out is a mixture of the A in and A in dagger, the AP out doesn't annihilate the vacuum state in the past. This means that we find some particles. So more specifically, if we define the out particle number density operator like this, which is defined by this, then this expectation value doesn't vanish. Actually, the expectation value is given by the the square of the beta p. And in this model, because we know the specific function here, parabolic cylinder function, and we can look at the value of beta p or alpha p precisely. And in this case, it is given by this form. So what we found here is that we find the particle production from the vacuum. So basically, the Chi particle were in vacuum, but we find the like a non-trivial particle number in the future. So this corresponds to the particle production from the vacuum. And this is, yeah.
I think I missed something, but you said that the vacuum changes. Vacuum is depending on time. So what if the corresponding vacuum? I meant.
I'm saying so I'm taking a Heisenberg picture. So we are evaluating everything by using the specific past vacuum state. Now, so okay, let me explain. Okay, so first we expand the quantum field like this, or this way. Then this operator corresponds to the annihilation operator for the past vacuum, so which I define here. And now by using the same equation, because of the difference of the asymptotic behavior of FP, we need to reshuffle the AP and AP dagger, so that you find the like coefficient of the FPWKB to be AP out. Then we find that the A out is given by mixture of the A in and A in dagger. This is what we found here. And what I said is that the in vacuum state is not annihilated by AP out, simply because it includes the AP dagger, AP in dagger. So this part annihilates the vacuum, but this part doesn't. So in general, AP out is doesn't annihilate the vacuum state. And what I said is that we can define the number density of the out particles. So we are defining the particle number by using this expression. And then we find that so state is, we are now evaluate the number of particles by using the in vacuum state. So we are always using in vacuum state to evaluate physical quantities. But now, in terms of the in annihilation and creation operators, the out vacuum is a mixture of them. So we find that the out number density operator gives some non-trivial particle number. I'm not so sure if I could answer to your question, but
thank you. It is very good. Thank you for your kind explanation. I understand what you're saying.
Okay, good.
Yusuke?
Yeah.
So here, are you interested in the vacuum in the out states, or I mean the vacuum state at t equal to plus infinity? The vacuum state is composed of particles. That is that your interest, and in the end you are considering particle production after reheating, then at t equal to plus infinity, right?
Right.
So instead of taking vacuum in state, you may have to take the vacuum state for the out state, right?
Not really, because we are story is like this. Our initial condition is the vacuum. I mean, we assume that after inflation there was nothing. So the physical state would be the vacuum for the in particles. I mean, chi was absent at that time. I mean, if we evaluate the NP in by using this, trivially it's 0. So this is the initial condition.
Yes,
but
initial.
What you see in the future is the out particles, because what we need to expand this field at the t to plus infinity. Then you find the different one. But of course, the initial condition was the 0 in. So we need to evaluate the particle number by using this state.
But at phi infinity, you have a different vacuum, and you want to define states based on the vacuum in the phi infinity. No?
Or you can think of in other way. 0 in corresponds to the some like a very non-trivial state in terms of 0 out. I mean, it's like some like a squeeze state or coherent state of squeeze state in terms of the A out. So meaning that 0 in is not a vacuum for the out particles. Yeah, of course, as we see here. Yeah, you can consider, you can like formally check the relation between 0 in and 0 out by using these relations, and then you find that in vacuum corresponds to the many particle states in terms of out.
Terms of out. Okay.
Yeah.
In terms of the vacuum and excited states.
So right. Exactly. Yes, that's true. Yes.
Mhm.
So in vacuum, it's a kind of excited states for the out vacuum.
Mhm.
Right. Exactly. Yes.
Okay.
Yeah. So that's why you find a particle from the vacuum. I mean, yeah. So we thought that initially that was a vacuum, but from the out future viewpoint, it's not really a vacuum. That's the point. Yes. Okay. Are there any questions?
Yes, just I want to confirm the T equal
Mhm.
minus infinity, because chi is produced from the phi particle, phi field.
Right.
So minus T equal minus infinity means that just after the production? Yeah.
Right.
Yeah.
No. It's just okay.
Mhm.
So first of all, let me
Mhm.
clarify this point. Now I'm using plus minus infinity as an approximation. Yeah, it's not really actual minus infinity or plus infinity. And also, I will okay. I have no like specific equation, but actually the asymptotic behavior changes at t equal t0. Yeah. So this point, I mean, when phi crosses the bottom, that's the time, and actually that is the time t0, and at that time, particles are produced. And in that sense, minus infinity corresponds to here, for example. And at the t equal to t0, the mass of the chi becomes it's minimized. And at that time, chi is produced. And again, this here is the corresponds to the plus infinity in my case. Yeah. So okay. So yeah, the definite difference of particle production takes place at the t equal t0. But to understand this, you need to know other methods. So yeah, it's not so easy to. But maybe you can look at the some like formula for the special function. And actually, when you continue this time to from positive, negative to positive, you need to some like analytic continuation here at the t equal to t0. And that indicates that particle production happens and its asymptotic behavior changes at that time. So it's a matter of mathematics, but actually physically that corresponds to the particle production. Yeah, this is another interesting point of this kind of thing. I mean, this kind of like a behavior of the special function have some like a physical meaning. So yeah, it's yeah. Anyway, okay, I said something too much maybe.
So
Yeah, thank you very much.
Yeah.
May I ask a question?
Sure.
Yeah, in the previous slide, I just wonder, just as you said, if you go minus t into to the plus t, there's there needs some analytic continuation. But just looking at the differential equation motion, it's a invariant and the sign change in time. So it sounds odd, right? So the equation itself is invariant under this parity.
Yeah.
But a solution that.
Right, exactly. But that's a very interesting point. I mean, so first of all, I took the initial condition for the f to be f so that it satisfies this kind of condition. I mean, in the past infinity, it becomes like a purely positive frequency, and in that, if you choose that, the future becomes a mixing of them. If you could choose different boundary conditions so that at the future the FP behaves like a pure positive frequency, then the past becomes a mixture of them. So in either choice, you would find this kind of like analytic continuation. I mean, different behavior. So it's very hard to say intuitively, but definitely we had some like a special how can I say, the understanding of why this is the case in terms of the so-called Stokes phenomenon, which I will mention later a little bit. So maybe I can say a little bit about that.
Okay, great. Thank you.
Yeah. Okay, thank you. Are there any questions? All right, great. Let me continue. So, okay, actually, this is a slide about, about Stokes phenomena. So, as I said, basically, what we saw, so the most important point for the particle production from vacuum was the asymptotic behavior of the mode function here. And so when in the past, this mode function is purely positive frequency, but after time t0, or some in future, they behave like a mixture of the positive and the negative frequency modes. And this kind of mixing corresponds to the particle production. And in mathematical language, we have a suitable language to describe it, so-called Stokes phenomena. And so I have no time to explain all details of this, but basically we can use like very sophisticated mathematics, so-called exact WKB analysis or WKB analysis to understand what is going on here. So roughly speaking, so what you need to do is that we consider like a complex file time plane. And you need to look for the place where this effective frequency vanishes. That is called the turning points. And from turning points, some so-called Stokes lines emanate. And in the Stokes phenomena corresponds to the mixing between positive and negative frequency when you close the Stokes line. So basically, when you close the Stokes line, there is a non-trivial mixing matrix A1, for example, here, and the structure of the A1 is determined by this function. That's the shape of the function, and the structure of the Stokes line is also determined by this function as well. Basically, you can determine all the property of the Stokes line as well as this constant matrix from this effective frequency function. Then once you determine, we find that when you close this line, you find the non-trivial mixing and again and again. So these correspond to the particle production from the vacuum in physics language. And so in that sense, if you analyze the Stokes line for this model, you'd find that at t equal t0, Stokes line crosses the real axis. So when you close this Stokes line, you'll find some mixture of the fk and f plus and f minus. So how can I say? And in the previous case, what I said is that the case with fk minus is 0. But because of this matrix, you always find the fk plus to be like some mixture of the fk plus and fk minus in this region. This is what happened in the previous case. And this happens even if you start from here. I mean, if you close the Stokes line in this way, you find some non-trivial matrix here. So whichever way you go, you would find some mixture of the positive and negative frequency modes. And these kind of issues have been applied to the particle production context in these papers. So I hope, you can find some like systematic understanding of Stokes phenomena from this paper or other mathematical papers as well. Anyway, the current understanding is that once you understand the Stokes phenomena, we can understand particle production from vacuum systematically. And this is a brief comment about Stokes phenomena. But I will not discuss the detail of this thing.
Okay, so whenever you cross the zero, you are producing particles. You need to change. You can make a Bernoulli of transformation whenever you cross the zero, right?
Yes, right.
Then
unless this matrix has a special condition. I mean, if this has some special form, it's possible that some mode doesn't explain particle production, but in general, no. Yeah, in general, the particle production always happen.
So as the Kunio commented, the quadratic approximation near T0 symmetry with respect to T0. So you produce particle if you go toward to 0, and then you are going to the maximum, and then going back to the origin. So when you you're producing particle again.
Yeah.
As you cross 0. So that is the case when you ignore the Hubble friction.
It's almost in it doesn't matter. I mean, even if you have
so do you think the amplitude doesn't matter much? And because the particle production also depends on the amplitude, right?
Right. Exactly. Yeah, it depends. I mean, so I haven't said any detail, but so the particle number produced from the vacuum is given by this formula. Now, the mu p squared corresponds to the bare momentum and the mass of chi. And the most importantly, phi dot. So it depends on. It's given by the exponent of the pi mu squared over square root of zeta. Phi dot. Yeah. So and this is a coupling. So first, the velocity of the field or amplitude of the field becomes very important in this sense. If this is very small, then this exponent just vanishes, right? I mean, this whole expression vanishes, asymptotes to the 0. So it's exponentially suppressed. But when amplitude of phi dot is sufficiently large, then this exponent can be sizable. In that case, NP becomes a sizable value.
Okay, so
in that sense, yeah.
So due to the initial condition for phi, the potential energy changes to kinetic energy. So because of the pi dot at T0 is determined by the amplitude,
right?
At initial time, and then if the amplitude doesn't change, you are keeping producing particles with the same rate, but the amplitude decreases as the universe.
I see your point. I see your point. Right. Okay. So I forgot to say various things. So yeah, as you say, amplitude is very important for particle production, and the inflaton experiences the damped oscillation. So its amplitude becomes smaller and smaller. That's why we could focus only on the first oscillation. Later time, it becomes just a smaller and smaller. If m chi is too small, this second event or third event, etc., could be important, equally important. In that case, we cannot neglect the other events. But m chi is almost the same as this maximum value, or this value. Sorry, this is a typo. This should be zeta square root zeta phi dot. And if they are comparable, then we cannot neglect the second or third. But something like that. I mean, eventually this effect becomes just negligible. So yes, and also I should have said that the interesting point is that this particle number formula is non-perturbative in zeta. So however you calculate the Feynman rules, you would never see this kind of particle number, because if you expand this particle number formula in zeta, actually you cannot Taylor expand this formula around zeta equals 0. So this is a very non-perturbative effect. So you never capture it from the Feynman rule calculations by scatterings, etc. So yeah, that's the second important point of this kind of phenomena. Yeah. Sorry, maybe sure.
Just another thing related to the humid question. You draw the Stokes line along the imaginary time.
Right.
I wonder what was the meaning of this, what was the role of this imaginary time?
It's just a matter of analysis. I mean, mathematical, very useful mathematical tool. That's all.
I see. So it doesn't mean if there's any what kind of decay channel or this kind of.
No, really, no, I don't think so. I don't think so. Yeah, at least what I can say is that this is a kind of useful technique. Yeah, it's very hard to give some meaning for this turning points, etc., because it's a complex fight time. So yeah, it's not really the like a complex energy for the decaying particle. So yeah, it's a different idea, I think.
Okay, thank you.
Or maybe you can find some interpretation, maybe, but at least I have no one.
Okay. Yeah, thank you.
Okay, good. Are there any questions so far? If not, let me continue. So okay, finally, yeah, this is the final point of the first part. So as I said, if chi is very light, then the second and the third oscillation becomes important. And actually, in the very first paper by Kaufman, Linde, and Stravinsky, they found that the particle number behaves like this. So first, like this step corresponds to the first event. But if the chi particle is sufficiently light, the second particle production become important. And it's not so like a clear resonance, but actually the amplitude or like a particle number of chi gets larger and larger, and it's exponentially large. So in that case, actually the back reaction from chi to phi, the background of phi, is not negligible. So in that case, typically we need a lattice simulation. But today I will not focus on such a regime because yeah, it's very complicated and it's very hard to extract some information analytically. So I just assume very simple assumption here. The velocity of and m chi squared is almost the same, so that the only first event becomes important. So remember that the mu p squared corresponds to, roughly speaking, m chi squared plus momentum squared. So if this condition is valid, since amplitude just decays, the second and the third events are just negligible in that case. Anyway, this is just a general comment about preheating. So I want to move on to the main topic, the QFT description of instant preheating. So what I have said so far is that the chi is produced from the vacuum. But next thing is the calculation of the scattering of chi to psi. This is what we're gonna calculate. All right. So first, this kind of process is known as instant preheating, first proposed by the fellow Kaufman Linde almost 20 years ago. And in this model, we just assume this kind of scalar fields. The original paper used like a fermions, but we will use a scalar field. And actually, okay, let me just remark on the this instant preheating paper. They used somehow like ad hoc calculation, I would say. They didn't give any like QFT calculation of this kind of process. And today, what I will show you is the kind of free QFT description of this kind of scattering process. Anyway, so what is interesting is that the mass of chi is time dependent. So because so when chi is created, the mass of chi is just very small. But eventually, the phi moves up its potential, then the mass of chi just increases due to this time. So it's like the chi gets fatter after some time. and then it can decay into other particles. And so I want to describe this kind of process using QFT. And so most important question is like this. So I think in the original paper, they assume the following. So because we have scattering amplitude in the flat spacetime like this, and we can calculate the decay rate from chi to psi, and then they seemingly assume that the decay rate in this case is given by something like that. You can naively introduce a time dependence for the energy to the decay rate. And then they could calculate or estimate the particle number produced from chi. So the number density of psi produced from chi and so on. But we are not sure if this kind of prescription works or not. So it's very naive. And especially, for example, this condition corresponds to the energy conservation. So it's a kind of kinematic condition for the scattering, this kind of scattering process. But we also know that energy conservation is violated because of the time-dependent background. So we are not sure if this should be the case or not. And in that sense, we need to check if this is correct description or not. And this is what I will show you next. So first of all, let me comment on the so-called Furry interaction picture. So the so-called Furry interaction picture was first proposed by him, the Furry, in 1951. And this is applied to the strong field QED. And in their field, in this field, many people use such a formulation to study the scattering process and so on. And this is what, so this is a Furry interaction picture. So first, we treat the strong background field as in non-perturbatively, and we consider the weak interaction between the quantum fields perturbatively. So it's just like an interaction picture of the dressed free fields. And this is the general structure of the Furry interaction picture. But it's not so complicated. For example, if you have worked on cosmology or inflation, you'd have you'd work on like calculation of the cosmological correlators, and then you consider the dressed particle. I mean the particles in de Sitter space, and that corresponds to the kind of dressed free fields. And then you can calculate the correlator by using the informalism, etc. So I think it's not so like it's not so how can I say non-trivial for cosmologists as well. Anyway, so what you need to do is to solve the dressed free field dynamics first. This is what we have done. And the next thing is evolve operators by interaction Hamiltonian perturbatively. And then, if necessary, we need a renormalization. And finally, we evaluate the physical observable, or we just take expectation value of them. That's all. Very simple.
What is the dressing means? What is the dressed?
Dress means that we had quantum fields coupled to the background inflaton, right? In that sense, chi is a dressed particle. I mean, dressed by the background pi field. That's what I meant by dressed particle, dressed free fields. Yeah, that's
the time dependent mass.
Yeah. Right. For example, yes. Yeah. Or like a redshift by the expansion, etc. Yeah, these things.
Okay, so.
Okay. Are there any questions so far? No? Okay, let me continue. So first, we need to solve dynamics of chi and psi. But for chi, we did it, right? We had like a free field expression like this, The next thing is psi, but once you so we neglect the expansion of the universe. So now psi is just a trivial free field. So I just assumed this kind of so we just neglected the expansion of the universe for simplicity or to get the exact result. But in general, psi energy could be time dependent as well. But due to the technical issue, I just neglected the Hubble expansion. It's okay if the mass of psi is sufficiently large. And yeah, then psi is not coupled. So I'm just assuming psi to be coupled to only chi, so not to phi. So in that case, the psi is just free fields in flat spacetime background. So this is this is very simple. So the mode function is just given by flat spacetime, like a positive frequency mode or negative one. And of course, this psi itself is not produced from the vacuum because it doesn't have any time dependence in the energy. This is the assumption. The next thing, we use like an interaction picture. That's all. And so this is the interaction Hamiltonian, and you evolve the operators chi hat, psi hat, from the free fields like this. So using the interaction Hamiltonian, you can evolve the operators. And interaction is just given by this cubic form. And today, I just focus on the number of psi particles. You can also evaluate the number of chi as well, but today I will not focus on it. And I only use the lowest order perturbation. So it's very easy to compute the part of the operator by using from this expression. You just expand this the Hamiltonian, and you just get this kind of formula. And once you get the psi like this, part of psi, then we need to define the so in general, sorry, yeah. First, you get the part of the quantum field like this, and then you consider the psi. You need to expand this psi field in the future, and we formally define the out operators, bk out and bk dagger out, bk out dagger, like this. So we assume that the psi is expanded in this way. Then we can relate this expression and this expression, or we can relate the bk. We can define the bk out in terms of this part of the operator by using the standard formula like this. So we just take t to plus infinity and multiply this flat space free mode function, and then this is just like usual, like del t on psi or minus del t on this one, and something like that. So then you can get the out creation and annihilation operator. So it's just a technical thing, and but a straightforward calculation. You can do this kind of procedure, and once you get the out annihilation operator, you can define the number density operator for the out. So out number density operator, like this, and you can evaluate it by using the zero in and zero in, zero in, and zero in corresponds to the vacuum for the B in, but now B out is different from the B in. So you find some non-trivial expectation value like this. This should be square, sorry, it's typo. And yeah, something like that. And now we have a FP, specific form of FP, parabolic cylinder function. We can calculate this integral, and you get this kind of expression. It's too messy, but this is the exact result. So now, okay, let me remind you that we had evaluated the particle number of psi produced from the chi through this interaction. And we got a very complicated but some specific equation. This is what we got. And so the next question is, how can we interpret this result? So we have like a psi number density, and can we understand from this Feynman diagram or not? This is a question we will ask next. Okay, so let me summarize my talk so far. How much time do I have to?
Including Q&A, you still have about 13 minutes, including Q&A time.
Sure. Okay. Yeah, but I think I can like finish in time. Okay. So far I have we had evaluated the particle number produced from kind of like a decay or interaction of chi and psi, and we got the particle number of psi like this. And the important point is that first chi is produced from the vacuum, and now we are discussing the fate of chi. The production, so the chi is produced from the vacuum, and now we are supposed to describe the scattering process of chi and the other particle psi. And to discuss this kind of process, we cannot use the standard Feynman rules, etc. Instead, we need to use a Fourier interaction picture, the dressed particle interaction picture. And also, because of this property, I think this statement is equivalent to this, but in vacuum state is not just like the zero out multiplied by some constant phase. It's not really the case. This is not the case. This is the case for the standard flat space-time case, but it's different in our case. So we cannot use the Feynman rule in Minkowski space-time. Anyway, so so far this is the exact expression, and next we will discuss its physical meaning and physical behavior then.
Excuse me.
Sure.
Yeah. First, you mentioned about the work of Felde-Akkermann-Linde, and their expression looks naive, and you get more rigorous results. So can you make a limit from this expression to their naive result?
Great question, and that is what I will discuss next.
Okay. Thank you.
Yeah, sorry, I have one question. So when okay, in my understanding, so because of the chi, the presence of the chi, the vacuum, the psi also changes. So the in vacuum of the psi is different from the out vacuum of psi, right?
Oh, that's also true. Yeah, that's true. Yeah, that's because we now have interaction between chi and psi. Yes, here. So right, the interaction. So chi. So yeah, that's true. That's true. Yeah, psi. Naively, psi is lives in flat space-time, so its vacuum is invariant under the time translation. But through this interaction, yes, right. The vacuum state becomes non-trivial for psi as well, right?
Okay, thank you.
So this
Any other questions?
unitary this time evolution contains Oberle-Overflow transformation for psi particle, right? Psi particle is addressed, but in the sense it changes the operator, how to say, the mode function changes in time for psi particle.
Yeah, not directly, but through the coupling between psi and chi. Yes. So psi 0 itself, so unperturbed mode function is just that given by the flat spacetime one. So as a consequence, if we turn off the interaction between chi and psi, then the vacuum of psi is just a vacuum. And,
actually, I'm talking about chi particles.
Chi. Okay.
Chi is dressed.
Right.
The mode
exactly,
function changes in time.
Right.
So when you consider time evolution, you are making some Bogoliubov transformation for the chi direction, right?
Right. Exactly. But also, if you turn on the interaction between chi and psi, psi would be perturbed as well. So
perturbative. Usual time evolution.
Yeah, perturbed by right. So now the psi itself doesn't experience any like non-trivial dynamics for the free case, but through the interaction between chi and psi, and chi is a dress particle. So through this interaction, the particle number, vacuum of the psi changes as well.
I see.
So yeah.
Then how did you include this effect in chi in your perturbative expansion? So is the chi just given as a function of time?
So now I'm using the non-trivial mode function, for chi. So this is a part of the dressed one.
I see. So I see. So you have an exact formula for the mode function.
Right, exactly. Yes.
I see.
Right.
It's a kind of interpolating between -infinity to +infinity.
Right. So okay. So let me remind. Let me give some comment. If you treat the coupling between phi and chi perturbatively, namely, if you just include this kind of effect perturbatively on the basis of just a free field, then you would never find this kind of process. Because as I said, the particle production is non-perturbative in theta. So any perturbative calculation cannot give the non-zero value for the chi particle number density. So, or it's very different from what we find here. So if you do the perturbative calculation, you'd never see this kind of expression, and this can never be understood from the perturbative calculation. Perturbative in coupling between phi and chi. I'm using perturbation for the interaction of psi and chi. But anyway, yeah. So okay.
Can you make a separation of production decay separately? I mean, can you make a produce once you chi particle produce and let them decay, and then so chi particle has a momentum distribution, and for given momentum, the produced particle, I mean psi particles, due to energy conservation, they carry certain momentum. And then you just integrate over the produced particle in the end.
Okay. Sorry, what was your question?
Because the production, I mean, if you have to produce chi particle first, right?
Right.
And then let them decay, and the decay rate can be computed based on the energy conservation for given momentum of chi particle.
So that's a that's a non-trivial point. I mean, of course, the spatial translation invariance exists. So the spatial momentum can conserve, but energy cannot in general. So you cannot find the 4-dimensional delta function in general.
Okay.
Yeah. Okay. That is somehow related to what I will discuss next.
Okay.
And I should say that basically, okay. Okay. Just I will continue.
Okay.
Yeah. So the next thing I will discuss is perturbative decay versus kinematically forbidden process. As you asked, so this is our first motivation. I mean, whether we can use this kind of like a flush space result to understand what happens in preheating background. So whether we can use the flush space-time result by very naive extension. And we will check if this is the case or not. And but first of all, as I said, if this extension is correct, then some instantaneous energy conservation should be satisfied. Namely, at some time t, after t0, this condition must be satisfied at some time t. But if we fix the momentum of the parent and the daughter particles, then or k and p, then it's not always satisfied. Because so in our approximation, the mass behaves like this. So if the daughter particle energy is below here, for example, then the mass or energy of the chi particle just increases. So this equality never satisfied. So if so, I can and indeed whether this condition is satisfied or not is a very important. I mean, if this condition is satisfied at some t, the particle production becomes like perturbative decay, which I call. And if this condition is never satisfied, it shows what we call kinematically forbidden process. And so roughly speaking, the difference is that the lowest energy of the chi particle is smaller than daughter particle energy. Namely, how can I say? If psi is sufficiently heavy, their energy is here, for example, then at first time chi is produced, but its mass increases, and at some point, this condition is satisfied. In such a case, we find the so-called perturbative decay, not so-called, what we call perturbative decay. And yeah, if the parent particle has sufficiently heavier than the psi particles, for example, the daughter particle has energy here, for example, then this condition is never satisfied. And in such a case, the kinematically forbidden process takes place. And actually, this perturbative decay is a very intuitive one. And this one is very non-trivial, I would say. So I will explain detail of these processes next. First, let me start with the perturbative decay. Yeah, if this condition is satisfied, and we can use the following approximation. So this is the exact formula, but to simplify this parabolic Seminar function, we can use some integral representation of this special function and the saddle point method. And under this condition, we find this kind of approximation. It's a little bit simpler, but still a bit complicated. So I will give you the different explanation or physical interpretation of this result. First, so let's start with the part of scattering amplitude from the flush space-time. And as I said, we find this kind of decay rate. So, and now this omega is time dependent. So we can just naively introduce the time dependence here. And we integrate over time. So that gives some total probability of this process for fixed K and P. And then we can estimate the number of particles, number of psi produced from this process. Oh, I find some chat. Okay. So, okay. So this is the this gives the total probability to for this process for whole time, and then we can estimate the number of particles psi produced from this process. Now, one event creates two psi, so we multiply 2, and the number density of chi is given by this formula. This is found from the previous the discussion about the production of chi. And then we multiply this probability. And then by performing this time integral, you find this kind of expression. This is nothing but this formula. So exactly the same. So this means that for the perturbative decay, where the energy of chi, okay, so the case where, oops, sorry, this kind of kinematic condition is satisfied at some point. In such a case, we can understand the process by using the Feynman diagram. So this is what we found. Yeah.
What is the C in the first line?
Oh, sorry, I didn't mention the definition of C, but roughly speaking, C is, where is it? C is this one.
Zeta.
Yeah, zeta times phi.
Okay.
Yeah.
So you're saying this parameter is responsible for the, how to say,
yeah, this one.
To get the original expression.
No, C is not important. Sorry, this, please neglect this one. Important point is that whether this
condition.
Yeah, whether this is satisfied at some t or not. I mean, if this okay, this is kind of intuitive, but okay, if we could understand, if we can understand the particle production in terms of this Feynman diagram, then there should be the energy conservation, instantaneous energy conservation like this, right? And this is satisfied. So the question is whether this is satisfied at some point or not. And in our approximation, the energy of chi just increases, right? I mean, this is chi is produced at this point, and then its mass just increases. So if energy of the psi are very, very large, for example, in that case, at some time, chi can decay into other two psis, or chi can satisfy this instantaneous energy conservation at some point, because the chi energy chi matches the that of two daughter particles. Yeah, in that case, we can use the Feynman diagram understanding.
Okay, thank you.
So in this case, there's some little delay of decay.
Yeah, in some sense, yes.
You have to wait until the mass, effective mass becomes large.
Right. Exactly. Yes. Right. And that was a kind of original motivation of the instant preheating. I mean, the energy of the chi becomes largest at this point, and the Kaufman-Linde, Federer Kaufman-Linde thought that at this point, the energy of chi becomes the maximum, and it gives sufficient or efficient energy transfer from chi to psi's.
Okay.
And in that sense, their analysis is pretty great. I mean, yeah, that's.
It looks forbidden. And from the beginning. Yeah, for zero amplitude of the inflaton.
Sorry.
For zero amplitude of the inflaton. The
zero
condition,
amplitude. Zero amplitude. Yeah.
If inflaton amplitude is zero, it looks forbidden. But
right. Exactly.
It becomes allowed as you increase inflaton.
Yeah. So okay, yeah, that's true. So in that sense, we should be careful about this approximation, because we have actual cutoff for the maximum value of mass. So yeah, when you evaluate the total particle number, then yes, yeah, you need to take into account this.
If total particle mass is too large, you cannot produce them. If they are too heavy.
Right, because yeah. But unfortunately, we are using this parabolic cylinder function approximation, so mass becomes infinite. So in that case, any energy of psi can be produced formally, but it's just an artifact. Yeah.
It's an artifact of approximation.
Right. Yeah. So what we have done is that the confirmation of the naive expectation. But the non-trivial thing, okay, sure.
You have 8 minutes, including Q&A. Just
Okay. Sorry. Yeah, I'll finish quickly. So the next thing is the case where the kinematic condition is never satisfied. That is the case if the psi is sufficiently lighter than chi. So daughter particles are sufficiently light. Then it's never. So for fixed p, chi cannot decay into tube size, because the energy of tube size is much smaller than that of chi. And in that case, energy conservation is not satisfied. So from Feynman diagram calculation, delta function support is not satisfied, so no particle production. But in our case, that's not the case that we found. So by using some similar approximation, which I used before, we find this kind of non-trivial particle number formula for this case. Then the very interesting and the non-trivial point is that in this case, particle number is actually non-zero, and also the exponent changes. So this fx is a bit complicated function, so I don't show the explicit formula for that. But the point is that so now x is defined like this. So the energy of the daughter particles and the ratio between daughter particle energy and parent particle energy. And when x is sufficiently small, meaning that the daughter particle has very, very small energy, then the energy of the So this f0 becomes maximum, and its value becomes half. And when x equals 1, it becomes 0. This is the behavior of this non-trivial function. And anyway, so first, so first of all, the surprising thing is the particle production is not particle production does happen, and naive Feynman calculation phase at this stage, because the Feynman calculation always requires the energy conservation. But obviously, this is never satisfied. But still, we find a non-vanishing particle number. And this is the consequence of the violation of the energy conservation. And that leads to this kinematically forbidden process. And so most important and the interesting point is that, okay, let me remind you that the number density of chi is given by this formula. But now compare with this one and this one, as I said, when x is sufficiently small, namely psi particle is sufficiently light, then this value becomes half. So compared with this the number density of chi particle, this is exponentially large in some parameter space. So meaning that the total particle can be much greater than the parent particle number density. And this never happens for the perturbative process because each n chi can produce only two of them, two of psi. So this condition should be satisfied in the perturbative decay case. So this is a very non-trivial consequence of the the scattering process in a time-dependent background. And okay, let me remind you how peculiar this is. So first, I assume that the chi particle has a direct coupling to the inflaton background, and psi particle couples to the phi indirectly through the interaction between chi and psi, like this. But through this kind of process, it's possible that the background creates psi more than chi. So this is an interesting new phenomena found from our work. And this is a kind of like, some numerical example. If we choose the m chi to be 10 to 15 GeV, and m psi to be 10 to 13 GeV, and the phi m phi to be 10 to 13 GeV or so, and the zeta to be 10 to minus 4, then we can estimate the energy density of the psi and chi in a similar way. So so far I just evaluated the number density of particle, but once you find the number density, you can easily estimate the energy density as well. And what you find is that the energy density ratio between psi and chi becomes 10 to cube or something like that. So now this is interesting because the phi is not coupling to psi directly, but the psi energy has more. And this is some like a Feno comment, but if we assume the reheating temperature to be 10 to 9 GeV, the energy density of psi can be comparable with the today's dark matter energy density. So this might be a possible mechanism to produce a super heavy dark matter, but I don't know. Yeah, we haven't studied any details of this kind of model. But anyway, this is just a numerical example. And this is not so important, so let me skip it. So, okay, let me summarize my talk. So what I have discussed today is the particle scattering process during preheating. And you need to discuss the Dulce particle formalism, which is given by so-called Fari picture interaction, Fari picture perturbation theory. And interestingly, the instantaneous energy conservation can be satisfied. In that case, you find the perturbative decay process, which is kind of like an extension of the naive Feynman diagram calculation. On the other hand, the violation of the energy conservation leads to very non-trivial process that I call kinematically forbidden process. And this process has some interesting properties. So maybe it gives new phenomenological application and so on. Okay, I think I'm running my time, so let me finish here. Thank you very much for listening.
Thank you very much. Thank you very much for your nice talk, Professor Yamada. Now open to questions and comments.
Hello.
Chen, both are okay.
Please go ahead. Please go ahead.
Okay, sorry, Chen first.
Okay, I have one question. So in your previous maybe the slide, the energy fraction of the rho psi is much larger than rho chi. I think that's I don't understand how it happened. In my understanding, okay, during some stage, if rho psi is close to rho chi, then all the energy of rho chi transfer to psi, then this process stop. So you know, when this oscillation happens and all the energy psi go to chi,
right,
then stopped. I think the energy density of rho psi cannot larger than rho chi.
right. Yeah, the point is that the violation of energy conservation. Yeah. So far, I first I motivate you to consider the scattering of the decay of chi to psi's. But because of the property of this formula, I don't think this is this psi produced by the decay of chi. It's not really I mean, I think you are imagining the standard Feynman diagram calculation like this. Chi energy goes to psi. In that case, yes, that's true. Energy is conserved at least instantaneously. So chi energy, so psi energy cannot exceed that of, or at least the original value of the chi energy. But it's not the case for the kinematically forbidden one, because, so for example, the number density of psi can be exponentially larger than that of chi. This never happens in Feynman diagram calculation. Yeah, it's very non-perturbative effect because, yeah, as I said first, C has C. So in the original variable, C is yeah. Oh yeah, C is given by the zeta times phi dot, and it's a non-perturbative effect between the phi and chi. So yeah, roughly, very schematically speaking, these scattering contains the infinite number of phi's, and that kind of assists the production of psi in a very non-perturbative way. So it's you cannot understand this kind of process from the expectation from the Feynman diagram type calculation. So I think yeah, it's a very mysterious yet.
I see. So maybe the psi gets some energy from phi, the inflaton field.
Right. Yeah.
And another question is, in the original case, if the mass of the psi is very large, and then all the energy transfer to the psi from chi, right?
Psi is very, very heavy. Yeah. Eventually, that could be true. Yeah. But yeah, it depends on the process. I mean, so for example, you can think of the chi psi and the propagating psi and the chi psi process. So co-annihilation of the psi, and that gives chi particles. That is possible in a late time if psi is sufficiently heavy. Yeah. Does it answer to your question? I mean, you asked the in the case of very heavy psi, whether you can whether psi can decay into chi, kind of inversely.
My question is about the total energy, even the energy from the inflaton. In the first case, it seems all the inflaton energy transfer to chi and then into psi. So the reheating happens just very quickly. But in the second case, the total energy of the psi, even a small fraction of the inflaton. So
that's true. Yeah, right.
So
exactly.
The reheating happens very slowly. That's the difference.
Right. You are right. I mean, yeah, total energy is still dominated by phi, the oscillation of phi. And so, yeah, that's kind of like a good good for our approximation, because I'm just neglecting the back reaction. But so in this case, reheating is kind of independent of this process. So yeah, we need to consider other channel of the decay of phi to some other light elements. Yeah, this the psi or chi cannot be a dominant contribution. But it's also possible that phi potential is not really a quadratic, rather it's a chaotic one. Then it behaves like a radiation. So its energy decays faster than the non-relativistic particles. So in that case, maybe these psi or chi, or in this case psi, can dominate the universe eventually. Yeah, it depends on the property of phi. I mean, yeah, how it behaves. But at least in this talk, I just assumed the massive phi. So yeah, in that case, we need to consider other channel for the decay of phi to complete reheating.
Okay, thank you. Very, very interesting talk.
Thank you very much.
Thank you. Next, Shuntaro.
I may ask a short question. This may be stupid, but do you think the role of chi can be replaced by graviton, for example?
Yes, I think yes, but okay, yeah, at least in this for this behavior, that's an interesting question. At least this non-trivial change of the exponent is independent of the size of the coupling between coupling between chi and psi. So in the case of graviton, I expect that this lambda becomes like m Planck squared. Some mass or momentum squared over Planck scale or something like that. So it would be very small, but still such a process might be possible. Yeah.
I see. You say,
but sorry. I think it's very difficult. Sorry. First of all, we need to create chi, right? And the coupling between phi and graviton would be also Planck suppressed. Then I naively expect that here, this exponent becomes very large. And this kind of non-perturbative effect would become negligible. Yeah, that I haven't studied such a case or non-perturbative production of graviton or gravitational waves, but naively it's super difficult.
Maybe the question
more.
can be rephrased differently. I mean, if you have a derivative interaction to inflaton, because the graviton through the energy momentum tensor is mostly derivative coupling.
Yeah.
For other cases, here you don't have a derivative in the interaction.
Right.
So.
So derivative interaction. Yeah, I think.
Like action-like particle, for instance.
So the question is, so interaction. So you mean the interaction between quantum fields? I mean, higher derivative. No, so the derivative coupling between quantum fields.
Between inflaton and some action-like particle.
Okay.
Chi is a kind of action-like particle, for instance. Then action-like particle can decay into standard model particles.
So, yeah, to analyze the if I try to for precise calculation, it's not so easy to estimate by from naive consideration, because as I said, okay, so non-perturbative production highly depends on this shape of the omega p. So the amount of particle is determined by this constant matrix, which depends on the shape of the potential or coupling, time-dependent coupling. So in the case of the coupling between axion and the other particle, for example, through the derivative coupling and so on, yeah, the shape of the omega p is different. But very naively speaking, derivative coupling is suppressed by some mass dimension for operator. And for the EFT, the momentum should be sufficiently small for the consistency. In that case, the effective dimensionless coupling between the effective dimension, effective size of the derivative coupling should be small enough for the consistency of EFT. So yeah, I expect that in that case, this zeta, roughly speaking, zeta becomes very small and this exponent becomes large. So non-perturbative production would become very small. That is, yeah, what I expect. But I'm not so sure.
There was some discussion about that, and then there's the validity. There's some range of validity. Perturbativity
so maybe,
and particle production.
Right.
Those can be consistent. In some cases, I mean, as you said, the library it is limited. Yes, the effective coupling is small.
That's true. But some case, okay, maybe related to what you mentioned. I mean, axion particle or axion, so axionic inflation case. It's possible to have the coupling between axion and the gauge field. In that case, yeah, many people studying the tachyonic, kind of effectively tachyonic production of the gauge field that leads to the chiral gravitational wave and so on.
You're right.
And yeah, in that case, yeah, the particle production is very efficient, although it's a derivative coupling. Yeah.
Okay.
But yeah, something like that. Yeah, there are many, like, it's kind of model dependent. I cannot say very general things. So it's yeah, that's a kind of interesting point of these things.
Yeah, I think that your discussion is the first step. So I think it's very interesting. So there are some questions. Other, like Pankaj, I think that he is waiting. The Professor also has a question.
Yeah, hello. Hi, so yeah, thank you for the nice talk. So I want to understand one thing is that in the original instant preheating work, one of the crucial thing was the presence of this fermionic decay channel. Because of the fermionic decay channel, the decay products could not form like the scalar condensate. But in your case, because you are decaying into a scalar product, scalar particles, so why not this condensate are growing? And if this condensate grows, then there will be no instant preheating, right?
So you're asking the condensate of
the scalar? The final products, because in the original case, Chi was decaying to fermionic channel, and fermions don't produce the condensate because of the Pauli blocking. But in this case, you are producing final products also scalar. So will not there be condensate of the scalar product? And then if the scalar,
that's an interesting question. But honestly, that's what I haven't thought of it. So that's simply I don't know. Maybe it's possible to form some condensate. That would be interesting. But at least even if psi forms some like a condensate, I believe that the inflaton, the ratio between inflaton energy and the condensate would be very small. Yeah, at least in this model. So in this parameter range. So in that case, yeah, it's negligible, but yeah, it might be interesting. I don't know. And also, I haven't mentioned anything about like conformation of this result, but I don't know, for the scalar case, maybe we can check by using some lattice or something if this kind of calculation is correct or not. But at least I would say the lattice calculation is a kind of classical calculation. So it might be not so useful to confirm this kind of quantum effects. I'm not so sure, but yeah. Anyway, yeah. So maybe, yeah, if some condensate or something formed, that's also interesting, but I'm not so sure. Yeah.
Okay. Thanks.
Thank you
very much. Professor Pyung-Ko?
Yes. Can you hear me?
Yeah.
Okay. Thank you very much for a nice talk. So I guess the inflaton pi can have a direct coupling to chi square. So how do you compare this inflaton coupling to chi to the effect you are describing?
Sorry, I cannot hear you well. I mean, could you say that again?
Okay. Can I write on the chat room?
Yes.
Okay.
So Professor is writing on the chat.
Yes. Now we can see it in the chat.
All right. So inflation can couple to chi directly. How do you compare it with this? Inflaton, yeah.
Maybe chi is psi. Do you mean psi? Because the
sorry.
Yeah.
Psi. So okay, simply I haven't introduced any like a direct coupling between phi and psi. And you are right that we cannot forbid such couplings because yeah, we have no way to, maybe some symmetry exists to forbid that. But at least, yeah, if maybe it's possible through the loop collection, for example. Yeah, that's an interesting question. I mean, okay. So yeah, that's a very interesting question. That's might be very important point. So as I said, phi couples to chi directly in my case, and the chi couples to psi. So in that sense, phi couples to psi indirectly. But if we integrate out chi, then what we will find is direct coupling between phi and psi. And then we might see this kind of production directory as like a direct coupling between phi and psi. But that kind of study has never been done. Been done. So I don't know. Yeah, that's a very interesting question. But yeah.
Did you see the comment? More comments?
Sorry. Oh, okay.
Yes. More comments. Psi mass will depend on the information. Yeah, if directly coupling. Yeah.
Right. Yes. Yeah. Exactly. So in some sense, how can I say? Let me show you the schematic picture. Okay. So what I meant is that I just close this diagram. Okay. So let's imagine like you prepare this diagram to one more and close psi and chi by considering a loop. Then you find a 2-point function of psi, right? Then phi directly couples to the psi effectively. And then the mass of psi would be time dependent as well. So that's what I meant by the direct coupling between phi and phi and psi, sorry. Yeah, that would be an interesting question, but loop calculation in this kind of background would be very difficult. At least I don't know how to do it. But that is my future direction. It would be interesting theoretical question and maybe phenomenologically interesting as well. Yeah. I'm not so sure if I could answer to your question.
Yeah, if there's a direct coupling to inflaton, you have to consider the non-perturbative analysis as you did.
Well, yeah, right. Yeah.
You have to go to the original discussion. Right?
Yeah. So in this case, the analysis was very simple because of this assumption. But if
here,
psi has a direct...
So instead of quadratic in the inflaton, if you have linear in the inflaton, then you have a phi square, chi-square coupling.
In that case,
it's like a scattering in your for chi, right? Case, but if you have a phi psi square,
phi psi squared, sorry, phi.
If we have a linear coupling in the inflaton,
yeah, but in that case,
square or phi chi square.
Yeah, phi squared chi might phi squared chi would be effectively the tadpole for chi.
I mean chi. Sorry. So phi
chi squared.
Chi square.
Yeah, in that case, that is also dangerous as well because phi chi squared. In that case, the oscillation of phi leads to tachyonic instability for chi as well. That is that may lead to the very efficient particle production of chi, because I mean, yeah, if phi is so this is linear in phi, then for large amplitude of phi, this mass can be positive, large positive and large negative. So that is known as a tachyonic preheating, and yeah, you can think of that process as well. Yeah, but in that case, particle interpretation would be a bit difficult for the regime of the tachyonic instability. So I simply avoid it. Yeah.
Maybe Pankaj, do you have any comment?
I think, I mean, if psi is directly coupled to inflaton, then I think this tachyonic instability and all this has been, I think, well studied by groups. So I think that will be the usual case of tachyonic instability or usual preheating, right? So. So I think those studies are already, I mean, there in the literature.
Right. Tachyonic preheating.
If this is already it is directly coupled to inflaton, then this are
Yes. So I think there was several works about
yes, there are several works. Yes.
So, but at least when I try to describe the scattering process, I wanted to avoid the like a tachyonic particle in the scattering process. That's why I didn't.
But in the end, you have a decay process for the inflaton. So I think that we are listening to several talks about preheating and then completion of reheating. So you have a scattering. Scattering only doesn't explain the completion. I mean, it doesn't explain complete reheating. So you need
decay also.
The decay process must be included, and you need to. It's necessary to analyze similar. I mean, this do the similar that coupling,
right? And I'm not so sure how important this kind of effect is for the real reheating. I mean, we don't know. Okay, at least in this model, this kind of instant preheating or kinematically forbidden process can never like complete the reheating. So in that case, perturbative decay would be necessary, and you need to think of perturbative decay process. But it depends on the, as maybe I mentioned it before, but if the phi is not massive, but it only has a chaotic coupling, or if inflaton is massless in a special case, in that case, I would expect some particle production due to the dynamics of phi, but it's the inflaton energy can decay much faster than non-relativistic particle energy. So in that case, like once you produce, for example, if inflaton has no potential, like it falls down to just like a flat land, and then in that case the inflaton, the universe experiences a so-called kination error, and in that case the inflaton energy decays like A to -6 or something, and it decays very fast. And in such a case, the particle produced by this kind of process would dominate the universe, and that completes the reheating. Yeah. So in that sense, it depends on the model of inflation as well as what kind of coupling inflaton has. So yeah, it's highly model dependent. So what I'm trying to formulate is kind of like a general process. When you have some like your preferred model. So yeah, this is a kind of first step to analyze the general model. So yeah.
Have you done the similar analysis for quartic potential? Like, instead of quadratic.
We haven't, but at least for the particle production, the free particle production, like this one, free field analysis like this. So I think Andre and collaborators worked on the quartic case as well in a very early paper, like around this time. And yeah, they found similar behavior, but it's a bit technically a bit different. But yeah, they found some particle production in that case as well.
Okay.
Yeah.
Thank you very much. Any other question? Or
I think if you are in CAU, I think we'll spend whole day about this discussion.
Yeah.
You should come to CAU next time.
Yeah, it's right. I feel there are no more questions, then we should probably close this Q&A time. So let's thank Professor Yamada again.